Hello, testing. Let's start. Have a look at the section outside posted. Try those questions already. One question. Yeah. Please do. Okay, please do. I think I got quite a good question from Chen. So before we go to the Taylor series problem that we need to solve on Tuesday, so there's a question posed by Chen. So we prove that if limit of the absolute of an go to 0, then limit of an also go to 0. Okay. So how we prove this? What did we use last time? Absolute convergence? No, this is not a series, right? It's just sequence. What's the theorem we use to prove this? Yeah, squeeze. So we use squeeze theorem. Okay, so squeeze by who? We have squeeze by which theorem? Squeeze by which sequence? I just squeeze an by absolute an and minus absolute an. Okay, if you can't recall, you should check back the statement here. So a natural thing we'll ask is the converse true or not? Okay, so Chen asks whether the converse is true. Okay. So what's the converse? So the converse is if limit n of an equals 0, then limit of n to infinity an is 0. Okay. By the way, I changed the set of color, hopefully more visible now, more pale now. Yeah. Yeah, so it's the converse true. Okay. He did a very good approach. Okay, he try a few examples. Let's try a few examples of limit of n go to 0, and then see whether this go to 0 or not. Okay, for example, one example he tries something like this. Okay, so very good approach is you try some examples. So for example, this one. Okay, but if you take absolute AN, what happens? Every guy go to the top, and then he say that I've tried almost all the example. I think this is true. Okay. So if you also have similar experience, then you should try and prove that this is true instead. Okay. Yeah. So how to prove this is true? Um, to show that this is true, we probably need more. Where we need more. Actually, we need the definition of limit. Is calculus one covering the definition of limit of the sequence of epsilon? No. No. Okay. So when do we say limit of n to infinity of an equal to some n? Okay. So we'll try and introduce the epsilon delta limit definition. Not delta, but epsilon n. Okay. So remember, last time I say, what's the definition of limit? Maybe ask how to remind us again. What's the definition of limit of the sequence? Keyword. What's the keyword? Close and large. Mm. So you have sequence, you have limit, and then you have close, you have large, you have n. So yes, correct. Okay. So how do we say this precisely? So what's arbitrary close? What is large enough? Okay. Max want to be precise. Okay, we want to make this into quantity. What is arbitrary? What is large? Okay. So what is arbitrary? What is large? So we say that an limit of an equals to L if for every epsilon greater than 0, okay, there exists an n, okay, greater than 0, such that for all little n greater or equal to n, okay, we have for all we have a little n minus L is less than epsilon. Okay, so meaning no matter how small I take this epsilon, I will find an that is arbitrarily close to L. Okay, no matter from the top or from the bottom. This is why we have the absolute value. Okay, no matter it's from the top or from the bottom. Yeah. But don't worry, this part won't be tested, but just an extra knowledge for you. But you will see this in analysis. Okay, in the next year. So just now our L is 0. Okay. Since limit of n infinity of an is equal to 0. This means what? This means for every epsilon greater than 0, okay, there exists an n greater than 0, such that for all n greater than n, that an is arbitrarily close to L. Okay, L is 0 in this case. Okay, an minus 0. In this case, an minus 0 is just an in particular. Okay, so what does it say? Okay. And then what's the statement you want to show? Okay, what's the statement you want to show? You want to show that limit of absolute an is equal to 0. Okay, so what's the difference here? What's the difference here? All the conditions should be just the same, but your sequence changes. Okay, so what's your sequence in this case here? Your sequence becomes what? Absolute of absolute an minus 0 is less than epsilon. But what is this? It's the same. Okay, it's the same. Okay, absolute an is less than epsilon. Okay, so you see, so given an epsilon, there exists an n. Where do you find the n? The n can be just the same n for an to converge. Okay, so you pick the same n. So let me put subscript an for here. Okay, so this is the n for an to converge. So how to find n for absolute an to converge? You just take n of absolute an to be equals to n of a. Then you will have this equality hold because an converges. Okay. Okay. Yeah. Can everyone read these or not? Can everyone read these this logic sentence here? So for every epsilon, you need to find an n such that for all little n greater than n, the condition hold. Okay. So I give you an epsilon, you need to find me an n. Okay. Yeah. This kind of question is what I encourage you to do, especially in my class. Okay. Because I'll see this as a transition to pure maths class. Okay. Because otherwise, if I just teach you how to calculate in this class, what's the difference of you and AIT student or engineer student? You get what I say? But there is a difference. They know AI, you don't know AI. But you know what they already know. So what makes you better than them? Okay. So what makes you better than them is your mind, your thinking. So you need to train your thinking, train your mind, okay, reading when you do pure maths. Okay. Is that okay? Okay. So please challenge yourself. Okay. Challenge yourself. Okay. So and when I say I ask you to ask question, right? So please ask because this is one part of my teaching process. If you don't ask, you miss the chance. Then something that you don't know, then you will miss it. Okay. You get what I mean? Like the senior, right? They don't like to ask. Okay. They just say, your assignment is very hard, very hard, very hard, very hard. But they don't ask. None of them ask in the class. Right. So if you think it's hard or what you don't understand, you should ask. Okay, this is actually it's part of my teaching process. Okay. If you don't use this process, then you will miss it. Like last time AIT, I teach similar, just without proof, but the style is almost the same. But they do exercise, they send me, I check for them. Okay, so if you don't gonna use this opportunity, you miss it, then you don't. Okay, so please ask, okay, and then please do tutorial question. Especially for those tests, you need to do quite a lot to get familiar with those tests. Okay. And then I think I posted out the review question for chapter 11. Okay, you can do those review question with solutions. Okay, so if you do the question, you check answer. it's different, then you can show me. Okay. Or you don't know how to do, you can show me. Okay. Or your solution is different from the solution, you also can show me if you are unsure. Okay. Yeah. Tutorial I can check. Okay, but assignment I cannot check because it's to test you. Otherwise, I would check everyone. So, right. Okay. Yeah. Okay. Yeah. And now it's already 4th week, right? Okay. Yeah, 4th week. So at the 10th week, you need to submit a project. So you should start thinking about it now. Okay. And then maybe next week, you should try and discuss with me what topics you want to do already. Okay. And then if we agree, then you go and do research. Okay. Then you have about 1 week, 1 month to write it out. Because after another 4 weeks, maybe you want to submit draft again for me to check. Okay, within the 1-2 weeks, you can check the draft for you, and then we can go back and forward. Okay. Because remember, we still have assignment who are and then test between these period. So please do it as early as possible. Okay. Okay. And yesterday the time actually is midnight, right? Is it a lot of you thought it's lunch time? Lunchtime. Huh? Yeah. Don't you see the difference between the paper one and the Moodle one? You trust the Moodle one. Okay. Yeah, luckily Seng come and talk to me. Otherwise, I don't realize also. Yeah. So yeah. So I mean, if you find any discrepancy, just ask me. Okay, and then we will see. Okay, just ask me. Yeah. But if you finish early, of course, good. But if you have any problem, just talk to me. Okay. Okay. I think we should settle the Taylor series first before we continue with Fourier series. Anyone thought about this Taylor series problem or not? Anyone think about it? Think about it. Okay. So what's the heck is going on? Okay. Okay. So the logic. What is the logic going on here? So first we come across the theorem. Okay. Come across the theorem says if F has a power series representation. Do you remember what's the power series? Linear combination of power of x. Okay. Power series such that f equals to sum of Cn of x to the power n. Okay. Then we can find the coefficient of Cn, okay, which is f to the n of a. So let's say this is center at a, okay, over n. So the logic is if you know the power series representation, then the coefficient is this fn. Okay. But if we go from a Taylor series point of view, okay, what we do is we define the n. What's the series name? Taylor series of f. Okay, Taylor polynomial, right? And Taylor polynomial of f to be what? To be the truncated. So let's call this Tn, right? So to be the truncated Cn, or the f to the n derivative over a over n. So many n, so let's change. Don't confuse, don't reuse. 0 to, okay. So let's say we don't know, okay, we don't know the power series of f, okay, power series representation of f. What we do, we differentiate once, twice, and then so on until n times, okay, evaluate at the center, divided by the n factorial, okay, and add the mark. We still have the power sticking on. Okay, so this is the Taylor polynomial. So for example, okay, for example, the example we work on is x. Okay, so let's say we forget about ex is equal the sum of xn over n factorial. Okay, so we forget. Okay, we forget this. So what's the first Taylor polynomial? What's the first Taylor polynomial here? So first, I think is T0, the 0, 1. Okay, so the 0, 1 should be just f to the 0 evaluated at 0 over 0 factorial. Is this correct? So let me move here first. So we want to evaluate ex at where? Find, let's say find, okay, find Taylor. Let's find the Taylor polynomial of ex. Okay, center at 0. Okay, center at 0. Okay, so what's the 0 term here? 1. Okay, so it's 1. How about T1? T1 is F0 at 0 over 0 factorial plus F1 0 over 0 factorial. Okay, so what's this? Sorry, we still need what? We still need a power on here. This 1 plus x. Okay, yeah. So can you see that? Can you see, or should we do one more? Let's do one more. So let's do one more. So what's the next one? So the next one will be added the second derivative. Okay. So the second derivative. Okay, what am I doing? So here is 1, here's 1, here's 2. So 0 square. Okay. What's the next term? So the next term is 1 plus x squared over 2 factorial. Okay. And then so on. Okay. And then you can see that actually this Taylor polynomial actually matches up with the first few terms of the power series representation of ex. Okay. Then, so how do you prove? How do you prove this? Again, how do you prove this? So one way to see is you check what is left over, right? Okay. So you want to see two things is the same. Their difference must be difference of two same things must be 0. Correct? Okay. But as you can see here, for power series of ex, right, it's not just the first few terms. There are still infinitely many terms. So how do we deal with those things? Okay. So how do we deal with those things? So we define again. Okay. So the remainder, I think the remainder for n Taylor polynomial f is what? Is just So let's denote this by Rn. Okay. N. Okay. So the remainder Rn for n Taylor polynomial is what? Is equal to f minus Tn. Okay. The leftover one I call remainder. So we want to show that this remainder go to 0. Okay, this is the key of the theorem. Okay, so what's the theorem again? So the theorem is if, okay, if what? If I know that my fx is tnx plus some remainder, and the remainder go to 0, okay, for, very important here, for what? For a region, okay, for a fixed region, then my f is also equal to the sum of its Taylor series at that region, okay, equal on that region only. On the same interval. Okay, so if you want to show f is equal to its Taylor series, okay, then you need to show that the limit go to 0. Okay, the first condition is easy to satisfy already because what? Because this is how we define Rn. Okay, this is how we define Rn. This is by definition actually, but the real works is here. Okay, Rn have to go to 0. Okay, but I don't tell you why this theorem is true. We just have to use it for now. Okay, if you are interested, you should look at the textbook. So our job is to show this part go to 0, and then we will see that f is equal to the Taylor series on the interval x. Okay, but you see, Rn is an infinite thing. How you control it? How do you control it? Then how do you control it? Rn is an infinite thing. Okay, and then not just Rn, one n is infinite. You need to consider the little n to infinity as well. You see what is going on? You got something left over, and then this leftover you need to consider infinitely many times. How to bound these things, right? So how to bound? Okay, so there's a theorem come to rescue called the Taylor's inequalities. Okay, so there's a theorem come to rescue Taylor inequality. Okay, so let's say I can bound every remainder. Okay, how do I bound it? I just need to bound the first term of my remainder. Okay, I just bound the first term of my remainder. So my first term in my remainder is this. Okay, fn plus 1. For within a region as well. Okay. Then my remainder will be bounded by the same constant. Okay, with some adjustment. Okay, with some adjustment. And then this adjustment actually is coming from the coefficient of Cn. Yeah. Is everyone following here? You following? You following? Okay, let's use the example, right? Let's recall the example from yesterday. So what do we do on EX? So let's go back to example on EX. Okay. So what do we do? So what's the let's let fx equals to EX. Okay, we look at EX. So what's the fn plus 1 of x? There's a reason why we pick this example here, right? Okay, there's a reason why we pick this example. Because when you differentiate EX multiple times, you still get EX, no matter how many times you do. So, let's say we want to show that EX is equal to a Taylor series. Okay. So our job is to use the theorem. We need to show that limit of Rn is equal to 0, where Tn is equal to the sum of n derivative evaluated at 0 over n factorial. Okay, let's don't use the same n, use I. 0 to infinity of x minus x to the I. Okay. Yeah, so how should we bound this Rn here? Okay. So what we're going to do is we use the Taylor inequalities here. Okay, we use Taylor inequalities. So what we do? So we can fix some d. Okay, we can fix some d. Fix some d, and then for x, okay, bounded by this d, we can also bound our n+1 derivative. Okay. So simply bound it by e to the d. Okay, simply bound it by e to the d. But this is repeating what we did on Tuesday. Okay. Yeah, so we bound it by e to the d. Then what do we do? Then by Taylor inequality, what do we have? Okay, we have Rn x bounded by e to the d. Okay, this is the m we are talking about in the Taylor inequalities, divided by m+1 factorial times x to the m+1. Okay, so the argument last time was this sequence here, okay, is bounded below by 0. Okay. But the right hand side here, if you take n to infinity, you also get 0. Okay, so by squeeze theorem, limit of Rn go to 0. So by squeeze theorem, okay, so I should say, so we say that the left hand side go to 0, okay, and squeeze theorem, limit of absolute of Rn also go to 0. Okay, is everyone feeling comfortable seeing this go to 0? Because this is a good nice step you need to remember. So x to the n over n factorial go to 0 when n go to infinity. And you don't need to prove this in your assignment or in your test if you're going to use this. Okay. Yeah. Okay. So this goes to 0. So by theorem, okay, by the theorem just now, okay, Ex equals to sum of Taylor series for x that's less than d. Okay, but we know that this Taylor series equal everywhere, converges everywhere, right? When we check for the power series. Okay, but this one only restrict to a d. Do you know how to picture this interval? No? You know how to picture this interval? What are the values that's less than d? So I guess we should fix a d greater than 0 here. Okay, then how to picture this interval? So these are all the value within minus t and d. Okay, and then our ex is something like this. Okay, ex converge to 0. Okay, so we actually know that it equals to Taylor series everywhere, right? Okay, so the problem is how to extend this. So first thing you can do is, of course, you can see that this d, I fix a d, there's no condition on the d. Okay, so I can fix the d as big as I can. Okay. Maybe I fix a very big d, 1 million or 1,000 million or yeah, and auto second and auto. Okay, but we still cannot cover everything, right? So how to cover everything? Don't know. You say don't know. No idea. Anything we can play around here? Okay. For every d, pick a. Uh-huh. Mm, sure. You can do that, and then you can do that. Then prove the d is, and then sure, this is unbounded, and then how do you deduce? You know the d, the range of d is unbounded. How do you deduce? Because why? Because why become a problem here? Because the theorem only tells you if you fix a d, the d work. It doesn't say anything beyond the d. You get what I mean? Yeah. Okay. So what you can do is you play around with this x. Okay, you can play around with this x here. Okay. You can move your x. You can move your x around. Okay. So you don't just fix x around 0. Okay, you can move your x away. Okay. Then if you can move your x away, you can imagine you can move this interval here and then slowly you can cover everything if it works for all x. Okay. Although you just work for a finite interval, okay, if you manage to move this interval infinitely many ways, okay, then you can cover the whole real line. Okay, so one thing to note here is, for the important upshot here is, wait, so note that the argument can hold for all x. Okay, yeah, not just x around 0. You can move it. Okay, yeah. So if you are curious about it, you should try and write it out. So not that the argument can be whole for x. Okay. Any question before we proceed? Any question before we proceed? Okay. If no question, then we will continue with Fourier series. We will continue with Fourier series. Anyone still remember what's the Fourier series? Still remember what's the idea of Fourier series? It's a series, first of all. Okay. So what kind of terms you are adding up? Don't know. Sine wave and cos wave. Okay. Instead of power of x, we are adding up wave. Okay, we are adding up wave. Cos wave and sine wave. Okay, we are adding up wave. So in particular, this kind of sine wave and cos wave, right? They are periodic. Okay, so let's give some definition first. So what we are studying here is a periodic function. Okay, so let's give definition. So a function f is periodic if there exists some p positive such that fx plus p equals to fx. Okay. So one example, few example you can keep in your mind is, for example, fx equal to sin x. Okay. So how do you see these equalities here? So you can plot out your sin x graph. Okay? And then this sin s will repeat. So where's the peak? So the peak is at pi over 2, and then the minus 1 point would be at 3 pi over 2. Okay, and then it goes to 0 at n pi. So here is pi, here's 2 pi, and 0. Okay. And then you can see that if you move everything by 2 pi, you get the same thing. So in this case here, what's the p in this case? What's the p in this case? 2 pi. Okay, the p here is 2 pi. Because if you move everything by 2 pi, you get the same curve. Okay. The p here is 2 pi. So this is a periodic. Okay. Yeah, sure. Then what? Okay, and then one more example, maybe you need to keep in mind later, we'll keep using it. So if I change my call frequency. So for example, we consider sine pi x over lambda or pi x over L, sorry, L and not lambda. These are periodic function with period. Okay. So why we care about this period? So later we will see. Okay, we'll see. So for example, so let fx be a function defined on an interval of 2L. Okay. So typically how you get periodic function? How do you get periodic function? Okay, so one way to get it is you have a function, okay, on the finite interval. What you do is you just repeat it. You just repeat it. Okay. So what do I mean by that? So for example, let's say I have a function. Okay. I have a function maybe look like this. Okay. How do I make it a periodic function? Okay. From L minus L to what do? I just repeat it, repeat it, repeat it, repeat it. Okay, and then I get a periodic function. Okay, so this is typically how we construct a periodic function. Okay, so this is what we call extension. So if I have a f defined on the finite interval, then f can be extended. Okay, can be extended to be a periodic function on R. Okay. So since it's a periodic function, okay, then we can use periodic function to approximate it. Okay, which is the cosine and sine wave. Sine wave. Okay. So this is what we call the Fourier series of f. Okay. So you see, not that how you read this sentence here. So here is the Fourier series of f. But this is not an arbitrary f. This f is coming from the f you extended. Okay. But you see, there are already few process coming already. You see, this f is no longer the original f. You see, so the original f is maybe just part of the function. Okay, part of the function. But we already extended the function. Okay, we already extended the function. Okay, so we extended the function already. So this f is actually talking about the extended version of the first f you see. Okay, but but here shouldn't have any. I mean, maybe we'll have some confusion, but should be easy to see. Okay, it should be easy to see that this f is considered as the extended f from the first f. Okay, is it okay or not? Because there's a lot of construction in analysis. It's like we want to extend the function. Okay, and then how you relate the extended function to the original function. So you need to be a little bit careful. What's the function we're talking about? Okay, whenever you see this. So what's the Fourier series of a periodic function? Okay, so what do we do? So the form it will take is we will write as capital F and little f on x. Okay, so you see, first series of a function is still a function. Okay, it's still a function. Okay, so the first term will be a0/2 plus n equal 1 to infinity of an cos n pi x over L plus bn sine n pi x over L. Okay. When I write this, right, you should first impression you should have is weird. Why is it weird? The left hand side has f, little f, but the right hand side no f. Okay, you should feel weird now. You get what I mean? Because this definition is defined with a little f. Okay, but there's no little f on the right hand side. Okay, so you should feel weird. So I'm going to tell you how to introduce this f into it. Okay, so you can see that there's a weird a0, an, bn. Okay, so you should think maybe the f should hide inside here. Okay, so in this case it's true. So where I'll define a0 to be 1 over L, integrate from minus L to L fx dx. See, fx is coming in already. Okay, and then an is equals to 1 over L, integrate from minus L to L fx time cos n pi x over L dx, and n equals to 1, 2, and so on. And then similarly for bn, we have 1 over L, integrate from minus L to L fx sine n pi x over L dx. Okay, so you can see that If I plug all these terms into my formula here or definition here, I'll get little f on the left and on the right. Okay, so only this definition makes sense. Okay, if there's nothing about f on the right, then we don't need f on the left as well. Yeah. Okay, so this is how you read mathematical definition. Is it okay? Okay. So we define as an integral of f. Okay. So you can see that these linear combination of cosine and sine, right? They are of different what? They are of different period, is it? Yeah, of different period because we multiply by n already. Okay? So these are really different, linearly independent cosine and sine. Okay, maybe you could ask, can we take power of cosine and sine just like how we take power of sine, x, right? Power of x are linearly independent to each other. How about power of cosine and sine? Power of cosine and sine. So this one need to use your trigo knowledge already. Okay. Power of sine and cosine, you can translate to what? So for example, cos A times cos B is what? Is cos A plus B plus cos A minus B over 2. Okay, so power of sine and cosine can be reduced to sum of cos and sine by changing the period, okay, or changing the point. Okay. Does it make sense? Hey, confused? Confused? Maybe. uh, okay, how about ask Larry to repeat? Larry, you got question or not, first of all? Do you have question on what I say? You don't think so? Okay, so can you like say again what I say?
Reduce them to sine and cosine functions with lower power and with different periodicity.
Yeah. It's okay. Don't understand. Don't understand, you need to ask because I don't know why you don't understand. Yeah, if you ask, then maybe I will know why. What's the problem? Oh, you don't know how to ask. Okay. So for example, okay. So for example, if I take power of cos square A, right? Okay. So what do I do? So I just reduce it to cos 2A over 2. So I reduce the power of cos into just cos. Okay, but I change the period here. Yeah, question? Cosine what?
A minus A where you plus 1, whatever 2.
Wait, what are you talking about? Oh, wait. Oh, okay. So I should have a plus 1 here. Correct? Yeah. Yeah. That's why I think, that's why I see why a bit lonely this formula. A bit lonely. Okay, hey, now this one makes sense already. Last time I used to ask where this one come from. This general formula here. Okay, good. Thank you. Okay, okay. So you can reduce higher power of cosine or sine wave to lower power until you just reach cosine sine. So that's why these become the linear combination. Okay. Of course, you need to deal with the sine square as well. There's a similar formula you should have. Okay. Okay. Let me. Okay. How about we just take a break and then we'll come back. Let's come back at 204.
很多 question
OK。
这个我要知道 T 一定是什么东西，然后是什么东西，然后我证明它是那个，就是那个 Taylor series，我要证明它是，我要知道它是不是一个 Taylor series 才可以做。我要知道它是不是一个 Taylor series，不是，是这个是不是一个 Taylor series？比如讲随便写，
你现在要做什么？你现在要做什么？你要做
证明这个跟这个是一样。那我不知道。
不是吧？不是这样证啊？不是。我记得这个题目是叫你找它的 Taylor series 嘛，对不对？
Yes，
这个东西是你懂的，不是要你证的。用这个去找这个的 Taylor series。
用这个去找这个的 Taylor
Yeah， 这个只是普通的 integration 罢了嘛。
Yes，
用这一个去找它的 Taylor series。
哦，
这个是懂的了，这个不用证的。
对，
不用 proof。
这样我是还有另外一个，
嗯
就比如讲嘛，
嗯
就讲我是，比如讲我是以那种然后类型的
嗯哼
N 几个 N 几个
嗯哼
20
嗯哼
这样子吧，
嗯哼
这是如果是这样子，如果是1，然后这是到1嘛，这几个到1，
嗯哼
然后
嗯哼
后来就是那么就是像 Rn，
，OK，R1
但是我这个就会等于这个，因为我可以随便选嘛，不是吗？
没有，是这样。这个 Rn 的 definition 是 EX 减掉 EN，这是我 define 的。OK， 所以我不知道这个一开始其实。这个是我们从 Power Series 那里知道的，然后现在我们是要从 Taylor Polynomial 来找。
用那一证明来找，
用这个来找，
哦，
用这个来找，就一步一步加上去，一步一步加上去，一步一步加上去呀，一步一步加上去呀。我不知道我不知道，我就假装我不知道它是等于这个，然后我一步一步加上去，然后我要 show that 我这样一步一步加下去，他们其实就是这个东西我要找，然后怎么知道呢？我要让这个东西去到0。
哦对哦，
呀，
哦，没有，
OK。Yeah.
So,
Mm-hmm.
previously you you say
Mm-hmm.
the what
Mhm.
stakeholder ratio
Mm-hmm.
can be considered as our project,
Okay,
right?
yeah.
But I just want to ask one
Mhm.
more time because previously
Mm-hmm.
we in our previous batch discussed about it during script mathematics.
Okay. And then
And then, yeah, so you don't mind lah.
What do you mean I don't mind?
Like deduce the formula for
What do you mean by discuss in discrete math? Is a project in discrete math? Or
we the lecturer demonstrated how it's derived.
Oh, okay. Okay. Yeah, fine. But I mean, your content have to be at least 1.5 pages.
1.1.
Yeah. So you need to make sure that you have enough things there.
Okay, because it's the first time I make this kind of project. Are there any requirements I need to do before starting writing?
What do you mean?
Uh,
You got. I got the format inside my course information. So what you need to put is like the key content and then example and then reference. Yeah. So other than the reference, they need to be at least 1.5 pages.
okay.
So if you after you derive, you think it's not enough, then you need to add some more related content into it. And then you will show us maybe how we gonna apply what you do, maybe in solving some math problem.
Okay.
All right. Maybe you have different way to prove the formula. Also, you can include all those. You get what I mean?
Okay.
Yeah. So you can maybe first way to derive this is this. Maybe second way to derive this is this. Third way to derive this is this. I believe there's a lot of ways. Maybe you can collect them together, and then your project will be different way to see Fibonacci sequences. Yeah.
奇怪的。
嗯
I mean，如果我是要找到这样一个
哼，
为什么会有？为什么会有啊？找这个吧，我们要让他
不是
懂这个。
这样子。我们一 start 的时候，我们只知道 Tn of ex，应该这样子，就是写上面 Tn of ex，我只知道这个罢了，我不知道我到底能不能写这个，我不知道。我不是 T 对哦这个就是重点，这是重点，这是 Tn 的重点。Tn 的重点就是我 define 它 as the sum of Tnf 的意思就是我 define 它为那个 f to the power n of x A， 因为我要 center 在某个点 A，x 减 A to the power 所以这里放成 I index 变 I factorial I 从0到 n 这样，这是一个 finite 的东西。
Yes。
所以我要 prove that 它等于它。
哦。
因为你在 infinite 之前，你肯定还有漏一些东西。
Yes。
所以是说漏了这个东西，我要让它 limit 去0，我才知道这两个东西是这样。
漏的东西，这讲漏掉的东西。
就是喂，说你看在每一个 layer 就是 T1 的时候，1减 T1 应该会漏，就是它 remainder 应该比较多嘛，但是 T2 应该是比较少的。如果它能够到越来越少到0的话，我才可以说它 limit 它跟这个去到 infinity 是一样，所以就是你写的这个东西的。对，现在因为有两种方法得到这个东西，一个是 power series， 然后一个是 Taylor series。所以 Taylor series 这个要 prove。
还有这个我知道哦，我讲一下，我它是不是很大小大于0，然后 exist n，那 n 是 am 嘛，对不对？n 是 am，对不对？这 n 是 fix，不是 那证明是啊，是那个刚才讲那个那个limit也是value，这个是那个点嘛，那也就是了。
不是这样讲，不是这样讲，就是说它后面的时候，就是说它在比如说这个是 L，它在这个切过后，它会在 epsilon 下，里面嘛，你就不会选这个当做 n，因为这边的东西就是前面的东西还大过这个 epsilon。
但这个 L 是哪？L 是哪
L 是它的里面，就是说，就是这个 an 会越来越靠近这个 L。等下再讲啊，如果需要的话。Testing. Okay, let's resume. Okay, let's resume. In the notes that I will provided, there are few integral. Okay, so there are few integral here. So for example, okay, if m not equal to n, which is greater or equal to 0, okay, and then you try and integrate cos n pi x over lambda times cos n pi x over lambda. Okay, so this thing is 0. Okay, so you can see that actually they are m and n is not the same, so they are like out of sync. Okay, out of sync, then you will integrate to 0. Actually, you can prove it. Okay, you can prove it using the similar trigo identity that I showed you just now, cos A times cos E. Okay, it's a good exercise if you want to show it. But I think I won't list all these down, okay, because we won't prove them or neither use them. But you will need them in the next assignment, I believe. Okay, you will need them in the next assignment. So you need to use them. Okay, so please check out these in the note. Check them out. Okay, we won't learn them, we just use them. Okay, we will just use them. So we won't spend time doing this. Maybe use them in assignment 2. Okay, we'll use them in assignment 2. Okay, next. Next thing is the convergence Fourier theorem. Okay. This one is important because later we're going to do calculation using this theorem. Okay, so if f and f prime are piecewise continuous, you know what's a piecewise continuous mean? You know what's a piecewise continuous mean? Waiting for my answer. So what's the piecewise continuous? So the function is continuous except at some discrete point. At some discrete points. So for example, what? For example, something like this. So my x and y is okay. So you can see that this function is actually not continuous, right? Because why? Because you have a jump. Okay, you have a jump. It's not continuous, but it is piecewise continuous. Okay, so it is not continuous except at discrete points. Okay, some discrete points. So if f and f prime are piecewise continuous, okay, at every point minus L to L. Then the Fourier series of F. So so F, capital F of little f at S0 within the interval will converge to 1/2 of limit of x to x plus. Okay, so let's see. So s plus from the right, and then equal to x0 from the left of x. Okay, so what is this doing? What is this doing? So let us read carefully a bit. So we have a f. Okay, we have f prime. Okay, we have f function. We can differentiate f prime. Okay, both of these are piecewise continuous at every point. Okay, at every point within the finite interval. Okay. Then you take the Fourier series. Okay, you take Fourier series, the construction we have just now. Integrate the f. Okay, integrate the f. So some of them you integrate fx, some of them you integrate fx times cos of some part. So some cos n pi x over L. And then the other you integrate fx times sine. Actually, I didn't say that this is equal to f, right? I didn't say this. Okay, so this is some maybe new function. Okay, we call it Fourier series of f. So we have a f, and then we produce another function called Fourier series of f. Okay, so how these two are related? Okay, these actually will solve our problem last time. Remember last time we says that we cannot draw a square wave. Remember, we cannot draw a square wave because square wave is not a function. Okay, but we can approximate these square wave. Okay, so we're gonna use Fourier series to do it. Okay. Okay, so let's look at example now. So that you have a picture what we are doing. Okay. So what to do? So consider the following function. Okay, consider a function which is 1 and 0, 0 at -1 to 0, and then 1 from 0 to 1. Okay, so what's this function here? So let's draw this function. So it is 0 from -1 to 0. Okay. Okay, wait, let me change. Oh, like this. This one. This is no better, is it? Differential cannot. How? So how? Yeah, make it flat. Okay, so 0 from -1 to 0. Okay, and then at 0, you jump to 1. Okay, you jump to 1. Okay, so this is a function like this. But for our case, we want a periodic function. Okay, so how to make a periodic function? So we have a function. This is not periodic, right? Is this periodic? No. Okay, so what we do, we repeat this this pattern. Okay, so how do we repeat this pattern here? So how do we repeat this pattern? Anyone want to have a guess? How do we repeat this pattern? What's the P we want to take? So we want to repeat the whole thing. So this thing is going from -1 to 1. Okay. So meaning if I go to -1, I should have the same thing as 1. Okay. So I need to make f -1 to be the same as f1. Okay. So what's the p I want to add here? What's the p? Make. So I want to make f -1 equals to f1. Okay. So what's the p I want to add to it? 2, correct? So if I make f -1 equals to f -1 plus 2, which is just f1. Okay, so we have to add 2. Okay, why is it 2? Why is it 2? Okay, where does this 2 come from? This 2 actually is the period of my function. Okay, 1 minus -1 is 2. Okay, so this is the period of my function. Okay, so if I repeat it, I'll get the picture something like this. Okay. If you like, there's a pretty picture in your lecture notes. Okay. Oh, this is a repeat. Okay, so this is the graph from, for example, from -3 to 3. Okay. Okay, so now we're going to find the Fourier series of this function here. Okay, we're going to find Fourier series of this function. So what's the formula? So let's bring back the formula. So this is the formula. So this is the formula. So meaning we need to compute the A0, AN, and BN. Okay. So we also need the formula for A0, AN, and BN. Okay. So I need to compute this. So let's make it smaller. Okay. So in this case here, you see, to create the Fourier series, we just need f within the L. Okay, within -L to L. So our -L to L in our case is just -1 to 1. Okay, -1 to 1. Hey, let's say what if let's say if I translate this -1 to 1, right? Okay, to maybe 0 to 2. Okay. Can you use the same formula? Yeah, I change the center, correct. I change the center. Right. Can I use the same formula? Because it seems like this formula center around 0, right? -L to L. Does it matter? Matter? Oh. Because you should create the same pattern, right? Just translate it. Okay. You see it in assignment 2 as well. Okay. Right. So now the L is from a -1 to 1. Okay. So let's compute A0 first, the constant. Okay, the constant A0. So A0 is easier, okay, because we don't need to deal with cosine sine wave first. Okay, we just deal with the function itself. Okay. So if I'm gonna integrate within -1 to 1, what happened? Okay, what happened? Our function is defined piecewisely. Okay, so meaning my integral need to split into 2 parts. Okay, remember the first part is just 0. Okay, the second part is 1. Okay, so this means that from -1 to 0, what's the integral? Just 0. Okay, right. And then from 0 to 1, I'll get something. Okay, I'll get something. So what is not Q is from integrate from 0 to 1 dx. Okay, which is just integrating x from 0 to 1, which is just 1. Okay, because what? Because when -1 to 0, it is Q. Okay, this is a piecewise function. Okay, so the constant term is 1. Okay, good. How about the an and bn? So we need to multiply with cosine and sine now. Okay, let's do the cos first. Okay, let's do the cos first. Okay. Okay, so you can see, here, all right? So why we pick this kind of function as 0, 1? Okay, you see, we need to deal with multiplication with cosine. Okay, let's say this fx is something else, x squared, x cubed. Then how you integrate? How do you integrate? Product of this. Sorry. Yeah. Partial integration. You say partial integration. You made partial integration. Yeah. Right. You need to use partial integration. Is it called partial integration? Yeah, integration by parts. Yeah, integration by parts. Right. Okay, you need to use integration by parts, or you need to use substitution. Integration of substitution. Okay. Okay. So in this case here, what happened? Similarly, from -1 to 0 is killed by the constant 0. Okay. So what do you left with? Okay, you left with from integral from 0 to 1. Okay, 1 times cos n pi x over dx. Okay. And then how do you integrate cos? You just get sine n pi x over n pi. Okay. Integrate from 0 to 1. And then in this case here, you will get yeah, what's sine n pi? What's sine n pi? Don't know. When is pi 0? When is sine 0? Huh? Sine 0 at 0, pi, 2 pi, 3 pi, 4 pi, 6, 5 pi, 6. N pi. Okay. At n pi, sine n pi is 0. Correct. Do you get what I said? Okay. Every time you should how you get what I'm talking about, you should have a picture in your mind. Okay. When I say sine, okay, you should have sine picture in your mind. Okay. You need to have the sine picture in your mind. And then where do you get 0? Exactly at 0, pi, 2 pi, minus pi, minus 2 pi, and then so on. Okay, so for the n pi, you get 0. Okay, so you get 0. So you get 0 for all n instead. Okay. Yeah. Okay, so how about Bn? Bn is also the same. Okay, Bn is also the same. So you integrate 1 over L. Hey, where's my L? Yeah, L is 1. Good. So -1 to 1 fx of sine n pi x dx. Okay. Okay. So what's going on here? So I integrate from 0 to 1 times sine n pi x dx. Okay. So integrate sine n pi x, we got cos n pi x over n pi and then minus. Integrate from 0 to 1. Okay, how about this time? What happened for cos at n pi? Alternate between -1 and 1, right? Okay, so how about let's keep it first. So what I have is cos n pi over n pi plus 1 over. So when cos n pi, right? So you need to have the cos picture again. So you have something like this. So when is it 1? It's at 0 and 2 pi. And then where is it minus 1? It is at pi. Okay. So if you extend it further, okay, you can actually see that it is 1 when it is even n pi. Again, it is minus 1 when it is odd n pi. Okay. So let me write this. So this is actually equals to 1 minus 1 to the power n over n pi. Okay. So when it is even, it is positive. Okay. When it is odd, it is negative. Okay. Okay, so this is true for all n in Z. Okay. Okay. But not that. What kind of n we need for an and bn? Okay. What kind of n we need? We just need n greater than 1. Okay, we just need n greater than 1. Yeah. Because if you put those negative 1 in, then maybe you repeat again some. You might get linearly dependent things inside. Okay. So we start with 1. Okay, so altogether what we have, so altogether we need to put inside this formula here. Okay, we need to put everything inside this formula here. Okay, we need to put everything inside this formula. So what is our A0? Our A0 is 1 over 2. Okay, plus n. Wait, let me check. A0 is 1, correct. How about AN? AN is 0. Okay, so finish. Q. So this one AN, Q, all the cost. And then what you're left with is the Bn. Okay, so Bn is 1 minus 1 to the n over n pi sine n pi. Okay. Yeah. What can you see here again? Actually, this is really similar to what happened last time. Last time we have the cosine and sine wave, right? So when cos is even, what's the power on the power series that survive? Remember? How do you write the power series for cos? Yes, with even power. Okay, sine with odd power. Okay, because cos is an even function, sine is an odd function. See what happens here. Who survives? Sine is an odd function. Okay, sum of the odd function is still odd. So it suggests that our Fourier series should be an odd function. Okay, it's an odd function. So you can see from the graph here, is it odd? Is it odd or not? Huh? Not really, not really. Why not really? Because how? Because it is not centered at 0. It's not centered at 0. But you can see the oddness here. You can see if I make if I translate it down, then you can see the oddness. But it is like an odd function, okay, translated upward. You can see so it's an odd function translated upward. Any question? There's something to understand in my statement, okay? Yeah. Because usually, okay, the usual definition is fx equals to minus x, right? Okay. So this is the usual definition. Okay. So if you have x here, and then fx, then you go to minus x, it should be minus fx. But in this case here, there's nothing in the negative side. Okay, why? Because I shift the odd function up. I shift it up. Okay. Is it? Oh, okay. Do you get what I mean? Hello? Any question? No. Okay. Jinsen, you got question? No? 跟我讲问 OK， yeah, try, okay, try, yeah, try. But do you get what I say? A little bit. So this is a shifted odd function. That's all I want to say. Shifted odd function shifted up. It's still odd. There's an oddness there. Okay. Okay. Yeah, so let me see. I think we haven't finished yet. Okay, so we haven't finished yet. So so next, what's this doing? What's this doing? You see, here is a sine wave, okay, plus a half, okay, plus a half. And so what's going on here? So sine wave is continuous wave, right? Continuous wave. But this function here is not continuous. So what is going on? Okay, so what's going on here? Okay, this sign here is continuous. Okay, so you have a linear combination of continuous function. So it's still continuous. Okay, but the f here is not continuous. Okay, so what's the relation between these two? Okay, what's the relation between these two? Okay, so like what I said last time. Okay, so you have a sine function, right? You have a sine function at first. Okay, so sine function is maybe something like wait, so something like this. So something like this. Okay. Okay. But it gets shifted up by half. So I shifted up maybe here. Okay. And then you add a lot of sine. Remember the example we have last time? I show you. Okay. So what happened is you form a continuous function at this discontinuity point. Okay. And so there's a question here. So the question is like this. So the question is, to what values does this Fourier series converge to at x equals to 0, at equals to 1, and at is equal to half? Okay, let's look at these 3 points here, 0, 1, and half. Okay, so where is 0? So 0 is the discontinuity point. Okay? 1 is also the discontinuity point. Half is the continuity point of my original f. Okay, so the question asking, if you have this Fourier series, okay, what happened at s equals to 0? What happened at s equals to half? What happened at s equal to 1? Okay, so how you cut through this discontinuity point? Do you cut through a bit higher? Or do you cut through a bit lower? You know what I mean? Both of them are still continuous, right? So how it cuts through? Does it cut through higher or does it cut through lower? Or does it cut through somewhere else and then come back? Okay, so this is at the discontinuity point. How about at the continuity point? Does it maybe go to this point and jump and then come back? Does it do things like this? Why are you so confident? Huh? Why are you so confident? Okay, very good. So sometimes you need this intuition. Okay, so is it true or not? Okay, So this is not true. Okay, not true by this convergence of Fourier's theorem. Okay, this Fourier's theorem tells you that how the Fourier series converge at the point. Okay, exactly using the limit of your original f. Okay, using the limit of your original f. Not only that, okay, it converges to the midpoint of them. Converge to the midpoint of them. So this is the half doing. So you add them up, you divide by 2. Converge to the middle point of the limit from left and right. Okay, so what does this mean using this picture here? So if you go to this discontinuity point, okay, where does it converge? It converges to the midpoint of the left and the right limit. Similarly, at x equal to 1, it converges to the left and the right limit. The midpoint of the left and right limit. Okay. So similarly, on this continuity point, you converge to the left and the right limit. The midpoint of the left and right limit. But left and right is the same. Okay. So you have 2 times the same number divided by 2 is the same number. Okay. Okay. So you see there's a symmetry involved when we try and I would say smoothen out these discontinuous okay, using Fourier series. Okay, which is good, which is nice. Okay. I like symmetry. Okay, that's why I'm in the algebra side. Yeah, algebra deal with symmetry. Okay. So what should we do here? Okay, let's talk so much already. So we need to do the maths. Okay, so how to compute this? So we need to compute Fourier series at 0, Fourier series at 1, Fourier series at half. Okay. So we have to use the theorem here. Okay, we have to use theorem here. So we need to use theorems here. What's the theorems? So the theorems is called the convergence Fourier theorem. Okay, convergence Fourier theorem. So for convergence Fourier theorem tells us that my Fourier series at that point is equal to the half. Okay, the half of the limit of my f. Okay, going to that point from the left and right. Okay, half of the sum of the limit going from the left and right of fx. Okay. So similarly, it works for all of these, where you just change your x. Okay. Or you just change your x. Okay. Maybe the picture a bit too far, so let us transport it down. Okay, so let's see. Okay, so I think we are in the same picture. Okay, good. So by convergence Fourier theorems tell us that the Fourier series at a certain point, okay, is equal to the half, okay, half of the limit of original f going from the left and right, okay, half of the sum. So for example, at f0 here, okay, x equals 0 here, it converges to half times going from the left, we get, what's the limit going from the left? We get 0. Okay. Going from the left, we get 0. Going from the right, we get 1. Okay. So it's half time 0 plus 1, which is just half. Okay. So this means my Fourier series go like this, and then cut at half. Okay. Cut at half. Okay. And then what else? f of 1. So going from the left to 1, what is your limit of fx? So taking limit of x going to 1 from the left of fx, what do you get? 1. Okay. Going from the right, you get 0. Okay, so you still get half. Okay. And then at f equals to half, okay, going from the left, you get 1. Going from the right, you also get 1. Okay, so it's a half times 1 plus 1, which is just 1. Okay. So meaning your Fourier series, when it cut through x equals 0, it cut through at a half. Okay, and then when it cut through x equals to half, okay, it cut through half. Okay, and then when you go down, it cut through half again. Okay, so it cut through the midpoint. Okay, so it looks symmetric. Okay, which is good. Okay, so let's say if you have to cut through different way, then maybe you need to devise the new things. Okay, maybe you need to devise new things. But Fourier series construction only give you points in the middle. Okay, when you cut through the discontinuity point. Okay. Okay. Is it clear about this convergence Fourier theorem? Is it clear? Any question? No. Okay, so maybe we continue. So, what's the use of Fourier series? What's the use of Fourier series? So, let's say, let's evaluate our Fourier series at x equals to half. Okay, let's evaluate this. What's our f again? So this is our f. Okay, so this is our f. What is our L? Oh, I haven't substituted my L yet. So L is 1. So get rid of this. Okay. So when x equals to half, what happened? Okay, when f equals to half, what happened? So what we get is 1 minus 1 to the n pi sine of n pi over 2. Okay, so what is n pi over 2? It's n pi over 2. What does sine does to n pi over 2? Start from 0 or start from 1? Okay, it should be start from 1. Thank you. Okay, so what does sine does at n pi over 2? 1 minus 1? Not quite right. You still have other terms. What do you have? 0. Okay, you go from minus 1, 0, 1, 0, minus 1, and then you repeat. Okay, so in altogether, what happened here? So for example, okay, so let's list down a few terms, right? So let's list down a few terms. So for example, this is let me move here. So this is half plus maybe 1 minus 1 to the 1 over pi sine pi over 2, and then 1 minus 1 pi to the 2 sine pi, and then 1 minus 1 3 pi sine 3 pi over 2. Okay, and then you will see that it repeats. Okay, it repeats. Okay, so what happened here? So what we said just now. So when it is sine n pi, okay, these terms disappear. Okay? And then, so the first one, what do you get? For the first one, you really get, what do you get? 1 minus 1, you get 1 over pi. Sine pi over 2 is 1. Okay, sine pi over 2. How about the sine 3 pi over 2? You get -1. And what's the coefficient here? So it's still 1 minus -1. So 1 minus -1 is 2, right? Okay, so 2 over pi times -1. Is it correct? Bit weird. So here we left out this n here. So here is the 1 times pi, 2 times pi, 3 times pi. So here 3 times pi. Okay? Is that okay? Yeah. So what's happening? So you can get, for example, the next term. Can you predict what's the next term? 2 over pi times 1 or -1? 1. Okay, and then the next term is 2 over 7 pi times -1 and so on. Okay, okay, good. Okay, so what are we going here? Okay, what are we doing here? So you see, this is the right hand side. Okay, how about left hand side here? Actually, we have computed this, right? Okay, this is 1. Okay, I even said this is 1. Yeah, this is 1. Okay, because 1 over 2 is at the continuity point. Okay, so in particular, just take the value of that. So this is actually 1. Can you see what we are trying to do here? Okay, maybe I move a little bit again. So I move this. So left with this weird guy here. So these all these weird guys have a similarity. What can I do? So I can move the pi across. Okay, and then all of them have a 2. I can move 2 away as well. And then what I get 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 and so on. Okay, what do I get? So what I get is I get an expression of pi over 4. Okay, so I write an irrational number in terms of sum of rational numbers. Okay, and then this series is what? It's an alternating series. Okay, alternating series of 1 over odd number. Okay, so now this is how we get the expression for pi sometimes. Okay, so in this case here, 4 pi is equal to 4 minus 4 over 3 or 4 times this series. Okay, so we get an expression of irrational number. Okay, using series. Okay, yeah. So this is one of the use of Fourier series. Okay. Yeah, so maybe I show you the picture. Show you the picture. Okay, show you the picture. It's the picture. Show you the picture. By the way, I put the Fourier series grapher, okay, the link inside the Moodle. So if you do exercise on Fourier series, you want to see the picture, right? You can go to the Moodle and then play with the link. So for example, this case here, this is the answer we calculated sine n pi x multiplied by these alternating coefficient. Okay, so if I add until fifth term, you will see something like this. Okay, of course you can see that this is cut through around 0, right? So you need to move. Okay, you need to translate it. This is what the constant term is doing. So the constant is shifting my sine wave. Okay, shifting my sine wave. And then if you add until 20 terms, you can see that it approximates better. Okay, approximate the horizontal line better. Okay, but you can see that it always cut at the same point. Okay, you can see that it's always cutting at the same point. Okay? No matter how much you add, it's still cut at the same point. This is the convergence of convergence Fourier theorem tells you. Okay, and then if you add more and more, it will approximate it. But this picture is a fake picture. You won't get this straight line. Okay, this is fake. So if you zoom in better, you will see there's a little bit differ from the straight line. Okay, maybe should we Okay, let's introduce some definition and then we will take a break or finish today. Okay, finish for the week. Let's continue. 2 more definition. So yeah, so we will introduce the even function. Okay, so a function is an even function. Okay, so we introduce it nicely now. Function on the interval minus L to L, if and only if f minus x equals to fx. Okay. And then why we introduce this? Because if f is even, okay, then across this interval, we don't need to do the whole integral. Okay, what we do, we just need to do half of it, okay, and multiply by 2. We just do half of it and multiply by 2. Okay. Similarly, for odd function, what happened with odd function? So it's an odd function on minus L to L if and only if fx equals to minus x. Okay. And what happens if we integrate an odd function across this period? What happened? 0. Okay, they cancel out because the positive area and the negative area they swipe out is the same. Okay, so the integral is 0. Okay, so for example, just now that one is even, right? It's at the top. Okay, it's at the top. So I mean, what do I mean by at the top? So you see, so this is odd function. Okay, this is odd function. But it doesn't satisfy fx equals to minus f minus x. Okay, so what you do? You can really shift this function down. Okay, you can shift it down. Okay, to see that it is really an odd function. Okay, I mean odd in the sense that you can find the Fourier series in terms of odd function. Okay, this is the odd I meant. Okay, not this odd function. Not this definition of odd function. Okay, I mean there's an oddness. Okay, there's an oddness in the function. Okay, what is the oddness? You can represent the oddness function in terms of linear combination of sine wave. Okay, this is what I meant. Okay. To be an odd function, you really need to satisfy this equation. Okay, but you see something similar to odd function, but it's not quite odd. Yeah, that one you need to be careful. Okay. Yeah. Any question? Any question before we finish? Okay, so please go back and do tutorial question and then find project topics. And then I will post out assignment 2 soon so that you can start earlier. Okay. If no question, then we'll see you next week.